Hi, I'm Norman Wildberger. Today we're going to have a look at the geometry of circles using rational trigonometry. So I hope by now that you've looked at all those videos up till now and learned all of it. Circles. There's one right there. Here's some basic terminology. Center of a circle. The quadrants of the circle. Well, that's not the radius, it's the square of the radius. A line through the center is a diameter. Another arbitrary line that meets the circle at 2 points is a chord. And this kind of line that just touches the circle in 1 point is a tangent. Important property of the tangent is that the line from the center to the point of tangency is always perpendicular to the tangent. Alright, so let's establish now one of the main results about a circle. And it stems from the extended spread law here. So this is the spread law, and it's been extended. If you go back 1 or 2 videos for the proof. What does it mean? Well, we have a triangle, and K is the quadrants of the circle that goes through them. There's the relationship between the spreads and the quadrants and the quadrants of the circle. Alright, so what we're going to do is we're going to fix a chord AB on that circle. And we're going to consider this point X on the circle as being arbitrary. Gives us a triangle, and we'll say that that quadrant there is Q, and that spread is S. Spread law here tells us that S over Q equals 1 over 4K, K the quadrants of that circle. So immediately from that, we deduce that S equals Q over 4K, which means that if you know Q, then S is determined. In other words, no matter where X is on the circle, that spread is always the same. We say that's the spread subtended by that chord. Now here's an important distinction, an improvement on the usual trigonometry. In the usual fashion, we deal with angles here. And then it's true that this angle is constant if you vary X here. But if you get to X on the other side of the chord, then the angle changes. With rational trigonometry, the spread subtended by that chord is constant no matter where X is. So our next result is one of the earliest theorems of geometry. It goes back to Thales, a teacher of Pythagoras. Thales noticed that if you have a circle and a diameter, so AB is a diameter, a line through the center, then the spread subtended by that diameter is always 1. Or in traditional language, these two lines are always perpendicular. That's always a right triangle. How does it follow from what we've just established? Well, if that's the quadrants K, then the quadrants of AB, since there's 2 of these, is 4 times K. And so this spread here is this quadrant, which is 4K, divided by 4K. Well, 4K divided by 4K is 1. So no matter where that point is, that's always a right triangle there. Alright, now to a little bit more sophisticated result that deals with the relationship between 2 spreads subtended by a chord. So we have AB, a chord of the circle, that's fixed. And there's actually 2 spreads that it subtends. One is from a point X on the circle, and we'll call that spread S. We know that spread is constant. And another spread that's subtended is the spread made by the lines to the center of the circle. Okay. Let's call that spread R. The relationship between R and S is this one here. R equals 4 times S times 1 minus S. You hopefully will remember that's the logistic map that comes about when you double an angle, the rational equivalent of it. Okay, what's the proof for that? Well, we look in this triangle ABC, and we use the cross law. 2 of the sides are K, 1 of the side we're calling Q. So K plus K minus Q all squared equals 4 times K squared times 1 minus that spread there R. Well, if you expand this, there's a 4K squared that appears on both sides, and they disappear. Then what's left over here is minus 4KQ plus Q squared. And on the right, we only have minus 4K squared R. So this equation here only has an r right there, so we can bring it to the other side and solve for r. r equals 4kq minus q squared over 4k squared. And now we just rewrite that a little bit. We take out that common factor q, take out one of the k's from the bottom, so write k over q, and then what's left over is 4k minus q on the top, divided by another 4k down there. What is k over q? Well, come back up here. Let me remind you that this spread S we've proven is q over 4k. So q over k is 4 times S. And what's in here is 1 minus q over 4k. In other words, 1 minus S. So that's r equals 4 times S times 1 minus S. And the last theorem today, the equal products theorem, which concerns two chords of a circle. And these two chords will assume they're not parallel, so they intersect somewhere. And then where they intersect determines altogether 4 quadrances. So we'll call that one Q1, and that one Q2, and that one Q3, and that one Q4. And it turns out this argument is not going to depend on where that intersection point is. It'll even work if the intersection point is outside. What's the theorem? The theorem is that Q1 times Q2 equals Q3 times Q4. So it's equal products. This times this equals this times this. Okay, let's prove it. So here I've drawn the circle again, a little bit bigger, which allows me to write down a few important spreads. Okay, so I've given things some names. There's still Q1, there's Q2, there's Q3, and there's Q4. Now this spread here, this spread S, is the spread subtended by this chord BC. Well, that chord also subtends that spread. We know, therefore, that spread and that spread have to be equal because it doesn't depend on that point there. In exactly the similar way, the chord AD subtends that spread R there and that spread R there. That's why we're allowed to say that's equal to R and that's equal to R. All right, now let's look at two different triangles, ACE first. We know two spreads, we've given them some names, and we have these two quadrances. Well, the spread law says that R divided by S, the ratio, is equal to Q1 over Q3. Usually the spread law is a little bit different. It's R over Q1 equals S over Q3. We're just rewriting it. In the triangle BDE, we have R divided by S equals Q4 over Q2, right there. And now we look at these two formulas. R over S equals this, and R over S equals this. So that means that Q1 over Q3 has to equal Q4 over Q2. And when we cross multiply, we get Q1, Q2 equal Q3, Q4. Next time, we're going to look at some applications of rational trigonometry to surveying. I hope you'll join me. I'm Norman Wildberger, and thanks for listening.